So welcome everybody for coming to this joint workshop with Riken AIP and EPFL-CIS. It's a great pleasure to have several very important researchers from Japan here with us, talking about machine learning and AI topics. I'll first actually thank some of the local organizers as well, Jan, Jocelyn, Nicola, Christelle. They did a fantastic job, and we have a very good program today. This evening, we will have a poster session, so make sure that you come for this one. And tomorrow, there's also a jam-packed session all day. Now, before I give the first talk, I would like to invite Masashi to give a brief set of remarks.
Okay, good morning. So first of all, welcome to the workshop, joint workshop today. So I'm quite excited to be here because originally, so we planned to come here in 2020 May to sign the MOU here actually. But it was unfortunately canceled due to COVID. And after that, we just postponed the workshop several times and we ended up in having online events so far. But finally, so we could come. So I would really like to thank everybody to host the workshop. So this is a great opportunity for us to communicate. Then the purpose of my first introduction is to explain who we are and what is RIKEN. So maybe this is the only slide I need to really explain. So what is RIKEN? So in Japanese, so our center is, our institute is called Rikagaku Kenkyūjō. So these 6 characters, and this is pronounced as Rikagaku and Kenkyūjō. The meaning is Physics and Chemistry Research Institute. And previously, I think RIKEN was in English called Research Institute for Physics and Chemistry or something like that. But okay, 6 characters in Japanese is too long for us to remember. And nobody call us Rikagaku Kenkyūjō. But people just take the first character, Ri, and the first character here, Ken. So combine RIKEN, like taking an acronym. So everybody calls us RIKEN, and nobody knows Rikagaku Kenkyūjō actually. So then at some point, RIKEN decided to use this RIKEN as the official name. So that means in English, RIKEN is not an acronym, but this is our official name. So this is where we are from. So then we are AIP. So RIKEN founded Center for Advanced Intelligence Project in 2016 under the Ministry of Education, Culture, Sports, Science, and Technology in Japan. So we are actually a 10-year project. So we are on the 7th year now. So it's great that we could finally come here. Then now we have about 130 employed researchers, and 40% are international and 25% are female researchers. So I think we have quite diverse center researchers. Then we have about 250 visiting researchers from universities and other industries. And also we have 130 domestic students as part-time researchers. Then plus, so we invited 140 international interns before the COVID days, but we stopped the internship program for the last couple of years. But this year, we resumed the program. So hopefully, through this workshop, we can have nice communication and hope that we can have some interns from EPFL also in the near future. Then also, we are very much interested in collaborating internationally, also collaboration with industry. And our office is located in the center of Tokyo. Actually, it's a walking distance from the central Tokyo station. So we are located in this building on the 15th floor somewhere here. And yesterday, Volkan brought me to the Rolex Center here. So that's fantastic, building and nice, decoration. And maybe ours is mini Rolex Center in this building. But we have a room like this, and we can accommodate visitors here, and researchers are also discussing and relaxing. And also we have talk here when we have guests. So whenever you have a chance to come to Tokyo, actually you need to always come to, I think, Tokyo station from the airport. Then, so our center is a walking distance from the station. So please visit our center. And also in addition, we have many teams across Japan. So from Sendai to Nagoya, Kyoto, Fukuoka. So depending on the team. So not only in Tokyo, but they are located in other cities. And I have some details, but maybe I just skip them. So thank you very much, and let's enjoy the workshop for 2 days.
All right. So the next speaker is me. So I changed the talk title a little bit. It's still about the same subject, but I'm gonna try to entertain you this morning. Maybe some of you know about this particular title that is like a Italian spaghetti cowboy movie, The Good, the Bad, and the Ugly. So we're gonna try to fit this particular theme. I also, before I begin, would like to thank Masashi and his team. Ikuko Sumora, they helped quite a bit over the years. We had these seminar series, these young star series, and so far it's been quite successful and popular. And I'm going to talk about some research, which is maybe a long culmination of several collaborations across the years, and it's good to acknowledge quite a few people. Now, let's begin with, so here I'm preaching to the choir when I talk about things like deep learning, but hopefully what I will tell you will make sense. So what I'll do is I'm going to talk about deep learning as an instance of supervised learning problem. So I'm going to use Vapnik's famous block diagram where you have a generator generating AI data features, a supervisor that is giving you some labels, BI, and as the learning machine, which is a pun on machine learning, your job is to learn a functional mapping between the data to the labels or the regression coefficients with some function h. And as opposed to looking at functions in all generality, we're going to parameterize it with some parameters x. And this will be a learning problem. Learn the parameters x so that you can try to predict what the supervisor has been trying to do. One way of doing this is to set up the quote unquote deep learning problem where you first restrict the function that you're interested in h into a, let's say, a neural network. Why? Because they're universal approximants, and a neural network is formed by just taking an affine transformation of its input, followed by a nonlinear transformation that is followed by then another affine transformation. And if you want to make this quote unquote deep, you just rinse and repeat and apply the same procedures over and over again. So given that we have, so you can take the layer matrices, biases and whatnot, put them into a vector little x, concatenate them. This will be the parameter that you're interested in learning. So how do you learn this parameter? Well, at least for the training data that we have observed, we want to match our predictions with the parameters that we have fixed to the data labels that are given to us, right? So the way we do this is by minimizing a loss function between. And given, let's say, n data samples, you use, let's say, the empirical risk minimization as a way of setting up your cost. And then once you can solve this problem, maybe you have some constraints on the parameters, you learn your, let's say, neural network that you will apply on test time. There are many loss functions, and of course, one can argue that whether or not this is the right thing to do, this is another question, but, like things like logistics loss, hinge loss, and so on and so forth has been popular. All right. Now, deep learning has shown quite a bit of impressive demonstrations, but within this, there emerged interesting grand challenges. And one of the grand challenges is their robustness. It turns out that given a trained, let's say, neural network, you can add imperceptible perturbations to human eye to radically perturb or change the decisions of the neural, these functions. And I think maybe many of you have seen these examples where you can take, let's say, this turtle image, and you can take a neural network that has, I don't know, superhuman performance on the data set, add, let's say, a little bit of perturbation that is not imperceptible to any human eye. Maybe a human would confuse this tortoise or turtle, but not necessarily a rifle, right? And that's what the neural network says that is. It's a rifle. And Tesla engineers also managed to show that you can take these stickers, put it on stop signs to make it look like a 45 miles per hour speed zone. So that's like catastrophic for any self-driving vehicle, because as opposed to stopping, you may be speeding up, which could cause issues, right? So what are these perturbations? It turns out that, these perturbations are actually deliberately designed. Now, one way to do this, and we're going to call this an adversarial example, is to think about the following. Let's say it's like a game, right? So you train your neural network minimizing loss. Now your neural network is out there, and somebody who has access to your neural network tries to figure out how it can perturb the input in a way that maximizes your loss. Again, we can discuss whether or not this is the right thing to do, but this is one way of basically designing these quote-unquote adversarial examples. You assume that the adversarial is somewhat limited in the sense that if the adversary has all budget, all power, then you're already screwed. But the subtlety here is to do this with very little budget, like this um, um, it is surprising that you can do this with very little budget. So one way to do this is to put, let's say, an infinity norm constraint on the perturbations with very tiny values of epsilon. You maximize this loss for a given input for your fixed neural network, and then you can achieve these feats. Of course, I mean, so here it turns out that these adversarial perturbations are unavoidable in the following sense that we are used to leveraging this blessing of dimensionality in problems where we know that there's concentration around the mean. It turns out that, you know, you can think about these high dimensional classification problems. The data basically somehow concentrates around the classification boundary that with little perturbations, you can actually take a large portion of the data and change these decisions. And that's what underlines the difficulty in let's say, adversarial robustness. But this has never been a barrier for machine learning researchers to do something about these hard issues, right? Like, to be honest with you, NP hardness has never been a barrier for machine learning researchers, for instance, right? So one way you can try to mitigate the issues that can come from adversarial attacks to explicitly train for it and say that, hey, as opposed to minimizing my loss, let me assume that somebody may be explicitly perturbing my inputs in order to make my loss worse. Now, again, we can discuss whether or not this is the right problem to solve. That's another issue, but this is the classical way of training for robustness, adversarial robustness. So here, the optimization problem will be something like this, that we have this, again, this finite sum minimization problem where the individual losses are implicitly defined through a maximization procedure, and that maximization procedure explicitly incorporates this adversary perturbing your input. So I hope this is clear. Now, given this, then the computational issues arise. So, okay, this form that we have on the left-hand side is something that the optimizers are very used to. It's this finite sum problem. This is like the bread and butter in stochastic optimization. But what is key in stochastic optimization is that at least you have a stochastic gradient. So one question here is that how do you get the gradient? Right? So, I mean, let me ask the audience, do you know how to get the gradient here? That we have a function, let's say fi, how do you compute its gradient? Okay, there are some comments. Well, so some of my students from Math of Data are raising their hands. So, I mean, if you don't know, you can take Math of Data, right? But this is something that we're going to discuss now, is that there is a way to get the gradient, and it somehow involves differentiating with respect to the maximization procedure here. Now, it is at this point, what I'm going to do is I'm going to introduce what is known as Danskin's theorem. And this is one of the most important theorems that actually underlines many of the optimization procedures that we use that involve minimization of minimax problems, let's say. And the particular variant here is from Bertsikas's thesis here. So let's say we have a function, a coupled function phi xy that has a maximization over the decision variable y, which is in some set S. Now, let's assume that with respect to the maximizer, there is a set of maximizers. So this may or may not be unique, right? So for a given x, right? So x is given. That's why this S star, which is the set of maximizers, the argument of maximizers, has a dependence on x. X is given. You're doing maximization with respect to this decision variable y. Now, the directional derivative of this function that is defined through this maximization procedure, an implicit function, along the direction of gamma, so you can pick gamma, is given by this maximizer, which is an inner product with the direction that you pick with the gradient of this function phi with respect to y, but the set that in which you optimize is the set of maximizers. All right, so this is a bit of a mouthful, and there's a lot to unwrap here. But the point that I want to make here is that if the set of maximizers is a singleton, right? So the problem is smooth, concave, and you have like one single optimizer. In the end, all you need to do is find the optimum of this function with respect to given x, find the optimum y star, take the derivative, and evaluate it at y star, right? But when you don't have a unique derivative, then you actually need to solve this particular problem. Let's not discuss how you get to this, but let's take this as a fact. Trust me, I'm a doctor here, right? So maybe I.
Do you have any assumption S star? Can it be a discrete set? Point-wise
So given that we're doing continuous optimization, maybe if it is concave, maybe we have a compact set. But if you're doing non-convex optimization, which we will talk about, this is the issue, right?
Mathematically, it's fine.
Mathematically, it is fine, but we will see further issues. Right, so the immediate consequence here is that if you had a unique maximum, then you can simply apply this theorem and you have the gradient. But if you actually take these adversarial robustness, in fact, and you can just initialize and run your whatever training procedure you have, you will see that. So what you do is, let's say you run it, you fix one perturbation, and then you initialize it with different initialization and just solve it a bunch of times. And you can look at the distance of each one of them to the very first thing that you found, right? Then you will realize that there's not a unique, it looks like there's not a unique maximum, that there's like a host of maximizers and it is not unique. So this is interesting, no? Okay. So I think this was 2019. Alexander Madry et al. Had this particular paper towards deep learning models resistant to adversarial attacks. And there, what they did is that, well, if you have it unique, you use what Danskin said. But if it is not unique, they argued with the corollary to Danskin's theorem that you won't get a descent, you won't get the gradient, but you will get what is known as a descent direction. So what I mean by that is very simple. So suppose you're at this particular point, the gradient will look at the contour, will take the normal with respect to the contour, and will try to move in the negative direction of the gradient, right? Whereas a descent direction at the same time means that you look at, let's say, the descent cone at the given point, and you pick any direction within the descent cone. So you have directions by which you can descend by appropriately choosing the step size. And in fact, sometimes descent directions may be better than the gradient direction, negative gradient direction. If you think about it, right? If you're thinking about the Newton direction, which is not the negative gradient for quadratics, this is like the best direction to descend. Does that make sense? Right? The Newton direction looks at directly to the minimum of the quadratic. Okay. But then is this really true? It turns out that it is not. So the corollary in this particular paper is wrong. In fact, this paper has been so influential that it is now in like textbooks. What we showed is that you can actually come up with counterexamples to show that you can get even ascent direction. So the corollary is just plain wrong. The wrongness, to be fair to the authors, is actually quite subtle because Danskin's theorem is used with signed direction. So there is the directions, the sign of the directions also matter. So this is the particular subtlety that they missed in their particular theorem. And what we show is that you can actually have ascent directions with the counterexample. So here, if you were to, with the counterexample, which I'm not going to get into the full details, is that you can have the adversarial training descend without descent, in the sense that some directions can be just plain old ascent directions, right? This is actually quite surprising. And what we've done is that we proposed another alternative way, in fact, something that Masashi kind of hinted at. what we did is that, given that you can run a bunch of these maximization procedures and get a bunch of points, right, not the full set, we said, well, okay, as opposed to using these points and doing discrete optimization, we just take the convex hull of those points and do the maximization procedure on the points, the set of points, set of maximizers that you already discovered. And that seems to mitigate the problem quite a bit. For the same counterexample, for example, this particular approach seems to do quite well. You get like this nice monotonic descent, and you can apply this to adversarial training problems in the in let's say what you have in the literature. And this kind of a training in terms of iterations can help actually in terms of your performance adversarial robustness. um, but at this point, I just would like to highlight the fact that the adversarial training is performant not just because you get this quote unquote ascent or descent direction using this maximization procedure, but it also does what is known as a graduate student descent, because these procedures have these step size schedules tuned in such a way that these step size drops and schedules, the warm ups, and so on and so forth, that I think that if you want to kind of compare fairly, you should also do this with what we've done. Yes. Okay. Now, so far, what I've talked about is mitigating computationally ways of helping out this robustness, right? But it is also important that this optimization, setting up costs is not the only thing, and there's an additional aspect that we tend to somehow assume in the kind of research that at least we do or we used to do in our group. It turns out that the architecture itself has a lot to say in terms of the robustness of the overall procedure or your functions, right? So just to highlight some of these things, I just want to set up some notation that I mentioned to set up this neural network. So here, I'm just going to ignore the biases just to make the notation a little bit cleaner, right? So when we talk about a deep neural network, we're going to talk about an L layer neural network. And now the L becomes not the loss, but the number of layers. I apologize for the notational mishap, but it is what it is. Um, so what we're going to have is that, so you start with your input and you apply your affine transformation one at a time. And there are some scalings here and there that is involved. So our parameters will be the neural network weights. So capital X1 to capital XL that are initialized by some beta, IID, let's say Gaussians, beta 1 squared to beta L squared. And so for the input, you will have beta 1 squared. For the output layer, you will have beta L squared. Just to make the notation a little bit simpler and the analysis easier, you're going to have the same initialization weights for the remaining layers. We're going to use ReLU. There are many other LU, whatever activation functions, but we're going to stick to what works best, ReLU. And again, we will avoid bias variables in the sequel. So what we're going to look into is a characterization of what we call as a perturbation stability. What this is just quite simple. You can think about the neural network, the input, and basically the first order Taylor expansion of the neural network predictions around its input, right? So if you think about it, if you take a little bit of a perturbation, a adversarial perturbation, the output changes quite a bit, right? Your prediction, let's say, goes from -1 to +1, right? And this particular first order term, and in particular its norm, kind of gives you an idea about how robust you are to these perturbations. But as opposed to looking at this in an adversarial setting, we're going to look at it in an average sense that, given an input, we're going to somehow take a ball around the input and look at perturbations that are randomly distributed. And we're going to take a look at how this particular expansion coefficient varies around the input. Does this make sense? This tells you how robust you are or how stable you are to perturbations. All right. And if you think about it, not everything is adversarial, and you should, in general, be robust in a little bit to noise. No, so this kind of captures the essence of this particular idea. All right. Now, just to set up another thing, we're going to talk about what is known as a lazy training regime. What that means is that suppose you initialize your neural network and you apply an algorithm, you look at the evolution of your neural network weights relative to where you started, right? And as your training time continues towards infinity, if the relative change is imperceptible, This is what is known as lazy training. All right, and this is a well-studied behavior, and one of the people, Linaik, will be giving a talk, also maybe related topics, but at least we have a chance to talk during the social event and so on and so forth today about these things. Anyway, so this is what I mean by lazy training. All right, for the interest of time, what we've done is to look at the impact of the architectures. What that means is that we're gonna try to understand how perturbation stability changes as a function of the number of layers, the width of the neural network, right? And it turns out that there's an ugly twist that is caused by the initialization as well. So what we're going to do is we're going to think about some of these initializations that give you different kind of initialization procedures, things like Lekan initialization, He, NTK, Cevher, mean field, and initialization. Now, for the case of lazy training, it turns out that there are interesting things. So first, what we can prove is that the width actually helps you in terms of your robustness. So this is very nice. Now, the depth can help you or hurt you depending on the initialization. So what we found is that with Lekan initialization, in fact, the depth can help you. Width, when you're in the under-parameterized regime, can hurt you, but when you go for the over-parameterized regime, starts helping you. The strand with the width remains with respect to other initialization like He and NTK, but depth swaps. That's what we mean by the good, the bad, and the ugly. The width is the good, the bad is the depth, and the ugly is the initialization, right? All right. So we looked into non-lazy training as well, but then you can only look at it, the two-layer neural network. The depth becomes a bit of a problem in terms of characterization. But let's not delve into this given the particular time that we have. And what we've done is that we've actually did numerical experiments to verify that the theory kind of matches the practice. All right, so let's not get into the details of this given the time. All right, so let's conclude. To be honest with you, even this particular simplified view that I presented to you today, it just makes it clear that robust and adversarial machine learning is quite challenging, right? So I've taken very dry, stylistic, theoretical approach to this particular problem that has really a grave importance to the machine learning industry and alike. But I didn't even talk about things like this, right? So when you do robust training, minimax training with non-convex, non-concave objectives, even the first order algorithms are susceptible to things that are known as limit cycles. Here, the robust training, for example, it seems to be related to the Lipschitz constant of the neural network, and there's hardness results for estimating the Lipschitz constants. And what I wanted to highlight is that some of the current paradigm of robust training, it works surprisingly. It descends without descent directions, but maybe it could be built on wrong foundations in the sense that maybe it's not the mathematical approach, but it's the graduate student descent that makes it work. And as we've seen in the second half of the talk, that the architecture, the initialization, the algorithm all jointly play a role. It's like raising a child, like there are so many factors that play a role in how good the child is going to be. Same thing kind of applies to neural networks. And what we've seen is that the over-parameterization helps robustness in line with this a law of robustness, this test of time award paper. And while looking at this, we managed to improve some of Zhang Jiangu's characterizations. And with that, I will end perfectly on time. If you have any questions, let me know. Yes. Go ahead, Musashi.
If you go back to page 12, the definition of the stability. So A hat is, A hat is over the uniform distribution on some ball. And is it the parameter for all layers? Or A is the input?
So A is the input, yes. we're looking at the input perturbation and not necessarily the weight perturbation.
What about X? So what's the distribution of X?
So X is trained, right?
So it's fixed.
So X is trained through, let's say, stochastic gradient descent with the input.
So what's the expectation over X?
Oh, yes, actually, maybe there's a typo here. Yeah.
You don't take the expectation. X is fixed.
I believe X is fixed, yes.
Okay. Then for the first part, so you have the result. So this one. So the right hand side, surprisingly, the PGD works quite well in there.
PGD is this black one. Yeah, so this is the standard training, and it typically works quite well, yes.
Yeah, so can you explain the reason for that?
So it is, again, these tunings that you do, these, let's say, step size drops seem to make the major difference, actually, right? But the thing about this is that, surprisingly, even in our counterexample, even though you get ascent directions, somehow it seems to even touch upon the minimum, right? I mean, this reminds me of this what was this, Ali Rahimi, who was arguing that sometimes to get to the minimum fastest is to take a stupid step size, just go away, then you converge better, right? So like he had some presentation at one of these NeurIPSs that he was talking about. So here maybe these ascent directions with non-convex optimization makes you ping pong around, and then you can maybe converge into the minimum better, right? So who knows, literally. But what I'm trying to say is that we need to be careful, because if you're trying to apply this to a problem which is well understood, you should know that you're not getting the descent directions that you think you are, right? That's the important part.
Other question?
Thank you for a great talk. So in the first part, I think you mentioned that in high dimensional space, many data are close to boundaries. But at the same time, I think many datasets are dominated by easier examples. And that means many examples are apart from the decision boundaries. So how can we understand these two things?
So the thing that I mentioned to you, this particular work by Tom Goldstein's group that argues that, so suppose you have a high dimensional sphere and your data is uniformly distributed over that sphere, and you can take the equator, cut it, and then you can take an epsilon slice around the equator. Then you know that because the data is uniformly distributed, it'll concentrate around the equator, right? So that's what I mean, that you will have this concentration around the decision boundary. And then with an epsilon perturbation, you should be able to swap the decision for any given data point. That is, so what you're mentioning is that the data is not uniformly distributed. Sometimes they're a little bit better distributed. That is precisely the reason things like this do work, right? So that's the contrast that I actually wanted to make. Yeah, no problem.
Thank you for your great talk. I have a question on kind of the things there has many empirical observations on how to make the curve looks like the DDD as you plotted. For example, gradually increase the epsilon over the training, or induce some randomness inside the training. For example, random flipping the labels. So I'm just wondering how your alternative way of computing the gradient connect with other empirical observations of.
So this is the thing, we didn't do the graduate student descent here, right? So we literally just take the methods and apply them as surmise. That's also what I try to explain, that you need to, if you want to get curves that are really nice, there's all kinds of tuning that people tend to do, which we didn't do here, right?
Oh yeah, that's
right?
excellent.
So also the cheating thing here is that this is with respect to epochs. If you notice, for the alternative way of doing this, you actually need to compute a bunch of gradients, right? So for the given maximization problem, maybe you solve it 5 times with different initializations, you get 5 solution points, then you solve a problem over the convex hull of those solution points to get the descent direction, right? That seemed to help, but this is like 5 times time consuming, except unless you can parallelize this and have 5 machines doing these computations at once. Then you can get the actual performance improvement in time.
I see.
Yeah.
Okay. Got it.
But
Thank you.
again, there's all kinds of tunings that get into this. Other questions? If not, maybe okay, Taiji.
Thank you very much for a great talk. So in the second half, so you showed some tables over there.
Oh, you mean?
Yeah, this one. So is there any lower bound? So is this just a upper bound? So, or in some
These are upper bounds, yes.
Okay.
I think looking into lower bounds would be interesting. I mean, for me, to be honest with you, the surprising thing was that with respect to Lecan versus Hay, the depth has a surprisingly different effect. But what I liked was that in practice, the practical performance somehow follow these bounds.
I see.
Right.
So, okay, so then I'm wondering kind of an intuitive explanation why the width helps for the robustness. I'm sorry, I don't get.
So to be honest with you, intuitively, I cannot explain. Okay. Right? Like we didn't even know that could help robustness until we've done the analysis and noticed that it could. So this is not a result where we first observed that it was helping and then we somehow took this quest of proving it. No, we were looking at this. We were more or less interested in this dichotomy between Zhang Gu's results and Sebastian Bubek's results. And while trying to do so, we kind of agreed with the Bubek camp, but also noticed that the initialization has this effect with respect to the depth that can swap. Yeah. So this is not necessarily an intuition guided result, but once we noticed that, once we had the theory, we noticed that actually it is matched in practice. Yeah. Sorry that I don't have the intuition for you.
Thank you.
No problem. All right.
Thank you, Volkan.